New York is a water-scarce city. Despite being surrounded on all sides by waterways and located in one of the rainier regions of America, the landscape upon which it was built lacks a significant supply of fresh water. To Manhattan's east, there's the East River, but its name is a misnomer. It's not a river. It's a tidal estuary, connecting one portion of ocean to another, letting them push and pull undrinkable, unusable salt water through. The Hudson River, to the west, does use the term correctly. It is a legitimate freshwater river, but by the time it arrives on the shores of Manhattan, it doubles as another ocean estuary. As the tides rise, seawater pushes in against the flow. The river only becomes usable freshwater somewhere between the Tappan Zee Bridge and Poughkeepsie, depending on season and conditions. That's to say, the waterways that surround New York City, that make Manhattan and Staten and Long the islands they are useless to quench the thirst of those living atop them. It's a perpetual irony.
Something is coming.
This location, at the head of one of America's greatest navigable rivers, attracted more individuals and industry than any other in the country. But that very location is the origin of its issues in supplying its populace with water. Strip away the skyscrapers of today, the brownstones of yesterday, and the streets of centuries ago, and you have a lumpy, forested island with one major freshwater source. Stretching across what are now 4 blocks in Chinatown and extending 60 feet or 18 meters below the ground, it was called Collect Pond. Some of the area's earliest indigenous villages laid on its shores, and so did some of the earliest European fortifications, but centuries on, after the Dutch left and the English moved in, tanneries, breweries, and other water-hungry businesses took over these same lakefront lots. For the burgeoning city, this proved problematic, as heavy use of the area's sole major water source made that same source unusable. The water was poisoned by the city around it, and so were the people. Wells were dug, but the situation was the same. The groundwater table beneath the grimy, gritty streets was hardly fit for human consumption. And beyond that, Manhattan was small, and so was its watershed. It was hardly sufficient to supply the growing population, let alone the population of today. New York City could no longer be self-sufficient. It needed the help of the mainland. If one were to hop in a car near the old Collect Pond today, go north on FDR Drive, cross the George Washington Bridge into New Jersey, bank north on Palisades Interstate Parkway, north again on Interstate 87, and exit at Kingston, New York, they will have driven for 2 to 3 hours, covered 100 miles or 160 kilometers, and though far beyond city limits, they'd find themselves within the jurisdiction of a New York City police department, just probably not the one you've heard of. This is the Ashokan Reservoir, one of the most critical and therefore most closely monitored pieces of New York City infrastructure. Here, in an area that receives some 40 inches of rainfall a year, is where the city has stashed an impressive stockpile of water in a series of rather unimpressive-looking reservoirs. These 6 reservoirs have a staggering 460 billion gallon or 2 trillion liter storage capacity and catch the drainage of some 1,600 square miles or 4,000 square kilometers of Catskill Mountain landscape. And yet, while the size is extraordinary and the adopted watershed's nothing short of essential to the city, it just doesn't look like much. In fact, what's so spectacular about these reservoirs is how thoroughly mundane they are. There are no massive treatment facilities, no towering protective walls, nor any Hoover Dam-like superstructures. Just a few large reservoirs surrounded mostly by forest, a few farms, and some quiet upstate hamlets. This is by design. In fact, this simplicity is the system's strength, and maintaining such simplicity actually requires quite a lot of coordination. Of the billions of gallons that pass through this watershed, not one goes through a filter, making the Delaware Catskill system the largest unfiltered water supply in the US. This distinction is a point of pride, but also the source of plenty of headaches. In order to meet stringent national standards set by the EPA and the Clean Water Act, New York City must monitor, protect, and prove over and over again the quality of this unfiltered water. Fortunately, the means for such heavy oversight were provided by the same 1905 state legislation that greenlit the Catskill Delaware project in the first place. Along with the reservoirs, the New York legislature also established the New York City Department of Environmental Protection to oversee city water and gave the city the power to regulate land use in the watershed so long as they provided local communities access to their system. Effectively, since 1905, New York City has had authority over what Catskill communities did with their land and put in the water. Hence the New York City police cars 2 hours away from the city. Today, to both ensure they meet quality standards and protect a logical terrorist target, the DEP staffs a 200-officer police department that patrols the watershed by car, boat, and even helicopter while maintaining a detective bureau and emergency service unit. But it takes more than a few cops patrolling reservoir borders to ensure that the unfiltered water is safe enough for millions. For this, the DEP employs nearly 1,000 scientists, engineers, and additional staff in the watershed to run daily tests in the reservoirs and their tributaries, and work with nearby farmers and communities to limit dangerous pollutants making it into the runoff. Every day, robotic buoys spread across the reservoirs take measurements on the water's turbidity, while labs run test after test to measure the presence of waterborne pathogens. While a tour of New York City's adopted watershed makes it seem a quaint pastoral landscape, these waters and the woods around them are closely monitored, heavily guarded, and teeming with DEP employees. But that pristine, clean water is of little use sitting 2 hours north in the Catskills. It has to actually get to the city. Now, transporting 1 gallon of water 120 miles or 200 kilometers is no challenge. What is transporting the sheer quantity that 9 million people demand. Every minute, the city consumes roughly an Olympic-sized swimming pool's worth of water, 680,000 gallons or 2.5 million liters. If one were to transport that quantity by semi-truck, it would take 71 of them, just for a minute of consumption. Of course, that's not the solution. What are two of the longest and largest aqueducts anywhere on Earth. The first is called the Catskill Aqueduct, a winding miscellany of dams, tunnels, and siphons capable of moving some 500 million gallons of water a day, 92 miles or 148 kilometers to the south. At the time of its opening, this aqueduct was heralded as a feat of engineering bested only by marvels like the Panama and Suez Canals. It was something that superpowers would boast of, built by a single city. But New York didn't stop there. 2 decades on, it became clear that the ever-expanding metropolis needed yet more supply. So, it built one single, continuous 85-mile, 137-kilometer tunnel. This was an inconceivable step forward. Before it, the world's longest tunnel stretched just 29 miles or 47 kilometers. This was over 3 times longer, and still today, the better part of a century on, maintains the title of the world's longest. It enters the Earth here, beneath the dam that holds back the waters of the Rondout Reservoir, and immediately plunges some 1,000 feet or 300 meters down, puzzlingly beneath the elevation of New York City. You see, while most think of aqueducts as a network of canals, bridges, and tunnels slanting slightly downward, modern aqueducts rarely take this form. There are myriad insurmountable obstacles sitting between the Catskills and New York City, so building a consistently downhill path with only a couple hundred feet of elevation differential between the reservoirs and the city would be an unbelievably complex endeavor at this scale. Conveniently, however, they didn't have to. The Delaware Aqueduct essentially operates like one giant inverted siphon. Now, the physics behind how siphons work is not fully understood, there are competing theories, but what matters is that liquid sent through a tube will always return to its source elevation regardless of the path of that tube. That's to say, water will flow upward against the force of gravity as long as the output of the tube sits below the input. Therefore, it's rather useful that the Delaware Aqueduct's origin, the Rondout Reservoir, sits some 545 feet or 166 meters higher than its destination, the Hillview Reservoir. The tunnel constantly changes elevation, avoiding obstacles, reaching its deepest point as it passes through the bedrock below the Hudson River. It then rises again to connect with the West Branch Reservoir, sinks, rises, and sinks again before reaching its final destination, but thanks to the principles that make siphons work, no outside forces are needed for the Catskill water to come out the other end. It's an entirely physics-driven transportation system. This aqueduct is incredibly efficient and effective, but also concerningly crucial. Nearly half a century ago, officials identified a leak in the stretch of tunnel spanning beneath the Hudson. Spilling tens of millions of gallons per day, the gush of water flooded nearby communities and counterintuitively contaminated their drinking water supplies. Authorities have been mitigating and managing the issue ever since, even paying residents to relocate away from the impacted area, but eventually, the problem had to be fixed. Doing so required 2 decades of planning, 1 decade of construction, and more than $1 billion in bills. A 2.5-mile, 4-kilometer diversion tunnel was built around the leakiest section, and in late 2023, the aqueduct will shut down for the first time in 65 years to accommodate the 5 to 8 month process of connecting the new section to the old. The shutdown was planned for winter, when water use tends to be lowest, but still, considerable work has gone into assuring the Catskill Aqueduct can operate at full capacity, and that typically minor water sources like the Croton aqueducts can ramp up to pick up the slack. With essentially 2 big pipes supplying nearly all of the water, the risk of failure in New York's water supply is uncharacteristically high for a city perpetually cognizant of the worst-case scenario, but is what's necessary to move such a quantity, such a distance from where it falls to here, the Kensico Reservoir. While sampling up until this point gives DEP staff a good idea of what's in the water, this is the first point where they act on that knowledge and add to it. This process begins at the exit tunnels of the Kensico Reservoir. Here, chlorine is first added to kill off any lingering microorganisms. Because chlorine levels dissipate over distance traveled though, chlorine is again mixed into the water supply at the nearby Hillview Reservoir, then for water headed all the way to Staten Island, again at the Richmond Chlorination Facility. Along with chlorine, the DEP also adds fluoride to combat cavities, orthophosphate to limit lead leakage from pipes, and sodium hydroxide to balance the water's pH level. Some additives are introduced to the system at static rates, while others are added in accordance to real-time water quality issues. In 2005, for example, when upper watershed rainstorms led to increased turbidity, the DEP added the chemical compound alum to the tainted supply as emergency treatment to lower particle level. Beyond additives, the DEP further fortifies its water supply here, at the Catskill, Delaware Ultraviolet Water Treatment Plant. Capable of treating nearly 2.3 billion gallons a day, over twice the city's daily demand, this facility is the biggest of its kind in the world, with its 56 UV pipelines adding another layer of defense against waterborne illnesses. But not all of New York's water goes through this plant, nor does all of it emanate from the pristine, protected Catskills. The other 10% of New York's water is still pulled from the Croton watershed, and unlike its supply sibling, Croton water requires filtration. Buried here below a golf course, air is added to the Croton water to float particles and salts to the surface for skimming before the same chemicals and minerals are added and the same UV process is employed to turn what entered as raw water into a consumable product. Effectively, the plant functions as a $3.2 billion one-stop shop that buttresses the Catskill, Delaware system by producing, at maximum capacity, up to 290 million gallons of potable water a day. New York's water supply is defined by billion-dollar projects and multiple structures deemed to be the longest or largest of their kind in the world, and yet the most intricate, expensive, and fickle stage may well be in final delivery. Once beyond Hillview Reservoir, treated water that began its voyage months earlier and 100 miles away won't see the light of day until it reaches a New Yorker's tap. Conveyed by tunnel and pushed along by system pressure, it's finally headed to a consumer. 3 tunnels supply some 9 million people with treated water. More accurately, these tunnels get close enough to every neighborhood in every borough for nearly 7,000 miles or 11,000 kilometers of water main lines to connect these tunnels with its 9 million customers, filling the city's iconic wooden water towers and pressurizing the taps in its pizzerias. While these very tunnels and the mains that branch off them are what allowed New York to bloom into a true megacity across the 20th century, today they are old, leaky, and breaking down. Tunnel number 1 was activated in 1917, number 2 went online in 1936, and today both are in need of inspection and likely repair. As for the lines connected to the tunnels, while the DEP reported in 2020 that its mains only experienced 5 breaks per 100 miles, a rate far below the national average of 25 per 100, it still reportedly costs around $400 million a year to repair all the city's busted pipes, a process made infinitely more difficult by New York's notoriously dense underground infrastructure, power cables to subway lines. Additionally, because of the age and varying quality of the pipeline supplying each city block, the DEP has spread 965 water testing stations around the city where staff pull samples each day and run over 34,000 tests each month. Delivery expenses don't end there, either. While operational, tunnel number 3 is still years away from completion, even though the project broke ground in 1970. Sitting 600 feet or 180 meters below ground and running 60 miles or 100 kilometers long, the tunnel has been called one of the most complex public works ever attempted and will be the city's single largest capital project, costing around $6 billion and scheduled for completion in 2026. New York is revered for its water. Locals boast about it constantly and even claim it's the key factor behind the city's purportedly exceptional pizza and bagels. But the defining factor of the system behind it is simplicity. It lets nature do the work of gathering and purifying, then uses just 2 tunnels and physics to transport it to the city. Counterintuitively, however, this level of simplicity is unbelievably expensive. Smaller, cash-strapped cities have not historically had the funds to design elaborate programs to protect their watersheds and build massive networks of record-setting aqueducts, leaving them with more marginal sources that today require more complex systems to make potable. But beyond the money, New York City had foresight, the ability to recognize that future stability, growth, and success all revolved around the task, simultaneously simple and complex, of getting good water.